Welcome back all of you. We were discussing about critical state models and we have finished Camp-Clay model and modified Camp-Clay model. And most of the numerical modeling adopts mostly modified Camp-Clay. So, in the next part of the lecture will be how to predict the failure state of soil based on the critical state model specific to modified Camp-Clay, and the procedure remains the same. So, we will have two lectures in this. The first lecture will be a general discussion on how to predict, and the next lecture will be specific to most of the matter remains the same, but then we will discuss with respect to consolidated drain, consolidated undrained for NC and HOC soil. So, this what we will be doing the next two lectures. So, it is all about prediction of failure state from modified Camp-Clay model. So, just to refresh, yield curve in modified Camp-Clay model is ellipse. We will not go into the details of it, this has been discussed. We have Q P dash axis, the first yield curve is marked, the yield stress marked as P dash y, the point where the critical state meets this yield curve, that is marked as M P dash y by 2, and we know that this is P dash y by 2. The equation is given P dash square minus P dash y plus q square by m square equal to 0. Soil is isotropically consolidated to P dash y, this one. So, this point, the same is shown here, P dash y, from where the unloading can happen. Soil is unloaded to P naught dash, which is a lightly over consolidated state. So, somewhere here, so that it is lightly over consolidated. So, P naught dash, this is the unloading line. So, you can see that it unloads to P naught dash. Now, I is the intersection of unloading line with CSL, this is the point, and that corresponds to this particular point. I is the point of intersection of yield curve with CSL. Now, all these information we have already discussed, and we also have the condition. So, without knowing MCCM, this lecture will not be good for you to understand. So, what are the properties according to MCCM? We know that P dash I is equal to P dash y by 2. Because these informations are needed for formulating the prediction. V at P naught dash is V naught. So, this is the starting point, because we are starting with an lightly over consolidated state. So, the V corresponding to P naught dash is V naught. So, this one. We can write this particular point of P naught dash as V naught is equal to V kappa minus kappa ln P naught dash from the equation of unloading reloading line, this particular line. So, V kappa somewhere here and minus kappa ln P naught dash. Now, this point V I we can represent in terms of unloading reloading line as well as in terms of critical state line. So, in terms of unloading reloading line, we can write V I is equal to V kappa minus kappa ln. We know that this particular point it is at P dash y by 2. So, that is P dash y by 2. We have V I is equal to V naught plus kappa ln P naught dash minus kappa ln P dash y by 2. From where it comes from, we are substituting it for V kappa. V kappa is V naught plus kappa ln P naught dash. So, that is substituted for V kappa. So, that comes to be V naught plus kappa ln P naught dash minus kappa ln P dash y by 2. and Vi can be written as V naught plus kappa ln P naught dash by P dash y by 2. Same thing is written. Now, based on critical state line, we can also write Vi is equal to gamma minus lambda ln P dash y by 2, the same point, but from critical state line. We can substitute it for Vi. So, when you substitute for Vi, we can write gamma minus lambda ln P dash y by 2 equal to V naught plus kappa ln, this particular equation comes here, P naught dash upon P dash y by 2. So, we can write gamma as V naught plus, you have lambda ln P dash y by 2 coming on this side, on the right side, that will be plus, and from here there is kappa ln P dash y by 2 minus. So, that will give us lambda minus kappa ln P dash y by 2 plus kappa ln P naught dash. Now, the knowledge of P naught dash, P dash y and V naught is required for MCCM prediction. Now, if the initial point is P dash y, so whatever we have discussed is for the lightly over consolidated point. Let us consider this particular point itself, that is the normally consolidated point. So, this is the point, this is normally consolidated and V is Vy. So, the initial condition is Vy. So, if that is the case, then Vi can be written as V naught plus kappa ln P naught dash minus kappa ln P dash y by 2. Now, here P naught dash, it is written in general. Now, our starting point here is P naught dash is equal to P dash y. So, here Vi can be written as, instead of V naught, the starting point is Vy, because it is a normally consolidated point. So, normally consolidated point, it is Vy here. So, Vy plus kappa ln P dash O is equal to P dash y, because we are starting point is NC. So, P dash y upon P dash y by 2. So, we can write Vi is equal to Vy plus kappa ln 2, because P dash y cancels off. Also, Vi is equal to gamma minus lambda ln P dash y by 2. So, that also we can write. So, here it is Vi is equal to gamma minus lambda ln P dash y by 2. If we substitute, we can get gamma minus, the same procedure for LOC, we are doing it, only the starting point is different. So, gamma minus lambda ln P dash y by 2 is equal to Vy plus kappa ln 2. So, gamma we will get Vy plus lambda ln P dash y by 2 plus 0.693 kappa, substituting it for ln 2. Now, gamma can be predicted based on the given conditions. If we know Vy, P dash y and kappa, which are the critical state parameters, gamma can be determined. Now, once gamma is known, then the particular critical state line is also defined. Now, let us come to a specific of drained triaxial test, like what are the failure stress from MCCM. Now, we know what are the failure stress, we are just trying to understand how we will determine the failure stresses based on the given MCCM model. Now, where is the role of MCCM coming into picture? Because the yield curve matters. So, with respect to any effective stress path, yield curve matters. So, that is defined in addition to what we have done in module 2, module 3 onwards. So, here we are adding another component while defining the failure state of soil, and that is yield curve. Again, soil is isotropically consolidated to P dash y, unloaded to P naught dash. Let us consider a case of LOC in general. So, we have P dash y, we have defined the yield curve corresponding to P dash y and critical state line, and then P naught dash. Up to here there is no need for discussion. Now, whatever is needed we have discussed till our last lecture. Now it is only summing up. So please follow the previous lectures very properly, so that we will be a bit fast in this lecture, and hence you will be able to pick up further. Slope of ESP is equal to TSP because it is a drained triaxial test. Now ESP from P naught dash yield at P naught dash y when ESP touches the yield curve. So it is this particular point where it yields, and the slope is 3. This information comes from our third module. Now this is the yield stress, that is P naught dash y, where it touches the yield curve. Now remember, the same discussion we have done in module 3. We do not have any idea about where it is going to yield. We just talked about the final state or the failure state where the ESP touches the critical state line. Now we are adding one more information, that is the yield stress. Now where the ESP touches the yield curve, that is P naught dash y. Deviatoric stress at yield is Qy. So that Qy is given. Soil fails when ESP touches CSL at F. So this is the point F. Failure stresses are P dash F and QF. So all these can be determined, like we can determine Qy P naught dash y. P naught dash y is written because the initial point is P naught dash, and the failure stress QF and P dash F all can be determined. Now looking at the geometry of this figure, that is, consider this triangle P naught dash F and P dash F. We can always write QF is equal to 3 into P dash F minus P naught dash. So it is very conveniently we can write this, and we know QF is equal to M into P dash F. QF is also equal to, considering this critical state line, we can write M into P dash F. So then this can be substituted and written M into P dash F is equal to 3 into P dash F minus P naught dash. So then rearranging, we can write 3 into P naught dash is equal to 3 minus M into P dash F, from which the failure stress can be determined, that is P dash F is equal to 3 into P naught dash divided by 3 minus M. You can see this particular equation where P dash F is the required failure stress. Now that is a function of P naught dash, which is the initial condition, and M, which is a critical state parameter. So once we know P dash F, we can determine QF, because we know that P dash F it is M into P dash F. Now for one additional condition which we need to discuss here is for M equal to 3. P dash F is equal to QF, which is equal to infinity. If you check here, what will happen to P dash F when you put M is equal to 3? So this will become infinity. So that is P dash F equal to QF equal to infinity. That means if at the particular point 3, if you remember our discussion earlier, like we have discussed about tension cutoff zone from the origin. When we discussed about this earlier in our previous lecture, we told that the same thing will be discussed later, how you are drawing a tension cutoff zone at an inclination of 3 from the origin. Now what will happen if M is greater than 3? If M is greater than 3, you will have P dash F to be negative. So for a line passing through origin and M greater than 3, both P dash F and QF will be negative, and that is the reason, and the soil cannot sustain tension. So hence M greater than 3 is an impossible state, and that impossible state is at an inclination of 3 we have drawn. Now anything more than this is not possible, because it will be negative and soil cannot sustain tension, and that is the reason we have defined it as a tension cutoff zone, another state boundary on the left side. So, that is the boundary beyond which the soil will not exist. Now, I hope the explanation is very clear and it is justified how we have drawn an inclination of 3 at origin and marked it as a tension cutoff or an impossible state of the soil. So, that is otherwise known as tension cutoff zone. Now, for the same case, undrained triaxial test for lightly over consolidated state, soil is again the same situation, P dash y unloaded to P naught dash lightly over consolidated state. So, P naught dash. The same is marked in the figure. So, the initial condition is fixed. Now, this is an undrained test. The very important fact that delta V or the specific volume, there is no change in undrained test. When this is the condition, we know that the initial specific volume and final specific volume, they are same. Now, this makes a lot of difference in our mathematical computation of failure stress. So, here the failure happens when it meets the critical state line, and that F is the failure point. So, V naught is equal to V F. Now, slope of ESP is 1 minus 3A, and we know that till yielding it is elastic. A is equal to 1 by 3. In fact, this particular aspect we have discussed several number of times. Now, what is happening is some bit of information is getting added all the time. So, it becomes almost very clear when we repeat these facts, but make sure like we are pointing towards the same ideal. Whatever we have discussed, the same ideas we are discussing, but in this particular case we are adding yielding coming into picture, but all these facts remain same. So, now for if it is elastic behavior, A has to be 1 by 3, when you substitute it, it will be infinity. So, it will be vertically upwards. So, ESP is vertically upwards. Now, once it yields, this is an undrained condition. So, the yield stress is P naught dash y and Qy. Now, after this it yields, and then what happens? ESP shifts towards leftwards due to positive pore water pressure. This is an undrained test. So, here the effective stress path moves leftwards. So, this is due to positive pore water pressure. Fails when ESP meets critical state line at F. So, we are not going to spend much time here because all these facts are known. Now, failure stresses are P dash F and QF, which need to be determined. So, QF and P dash F. So, this is the failure stress. So, that is for undrained test for lightly over consolidated. Now, let us see undrained triaxial test for heavily over consolidated. So, soil is isotropically consolidated to P dash y and then unloaded to P naught dash, the same procedure, but the unloading is much higher. So, P dash y yield curve, critical state line. Now, you can see that it is slightly towards the left end because it is heavily over consolidated. The same is marked on V ln P dash plot. You can see that this much is the over consolidation that is happening. V naught is equal to V F, delta V is equal to 0 in undrained test. So, V naught is equal to V F, slope of ESP is equal to 3 upon 1 minus 3A. ESP till yielding is elastic, the same information, yield when it touches the yield curve. So, up to here it is all clear. So, this is Qy and P naught dash y, the yield stresses. After yielding, ESP shifts rightwards due to negative pore water pressure. Again, it is a known fact, fails when ESP meets critical state line at F. So, that is F, it is undrained test, so it meets at F, and P dash F and QF are the failure stresses. Now, equation of Mccm yield curve is this. Now, we know that this effective stress is meeting the yield curve. So, if you substitute this particular point, we have P naught dash square, that is we are referring to this particular point minus P naught dash P dash y with respect to the initial point. So, here P naught dash is equal to P naught dash y, that also we need to keep in mind. So, we are writing in terms of P naught dash right now. So, that will give us P naught dash square minus P naught dash P dash y plus Qy square by m square equal to 0, where ESP meets the yield curve. In this particular case, Qy is defined by the yield curve, can also be considered as Q peak. Now, keep Q peak is the state boundary for heavily over consolidated soil. You might be remembering this very well, like in our previous lectures we have discussed with respect to peak point of for a heavily over consolidated soil. So, what happens, the soil, the stress strain response increases, it reaches the maximum, that is the peak point, and then strain softens. Now, what we have drawn is, we have drawn a peak line and then it touches. So, the maximum point to which the soil can reach, as a heavily over consolidated soil can reach, is the peak point. So, here in this particular case we are defining it by means of a yield curve. So, here if you consider yield curve to be same as the state boundary surface, then you can always approximate yield point to be that of peak point. In fact, that is depending upon the critical state model. Now, whether the soil actually yields at that peak point, this is not very clear. It can yield slightly before or maybe slightly after or maybe at peak, this is not very clear. But here we are assuming the yield point to be same as the peak point, because both serves as the maximum point, state boundary point. So, that is why, so Q peak is the state boundary and hence Qy, that is the yield point, this particular point can be considered equal to Q peak. If that is the case, we can write Qy square upon P naught dash square m square is equal to P dash y by P naught dash minus 1. What we are doing is, we are dividing it by P naught dash square. So, here we will get 1 minus P dash y upon P naught dash plus Qy square upon P naught dash square m square. So, when you bring it to the right side, we will get this particular expression. So, then Qy, that is the yield deviatoric stress, can be written as m into P naught dash root of P dash y upon P naught dash minus 1. So, this is a quick way of computing Qy, and we know that P dash y upon P naught dash is nothing but OCR with respect to the initial point. So, P naught dash, that is P dash y upon P naught dash, is nothing but the OCR. So, you can replace Qy is equal to m into P naught dash root of OCR minus 1, and this is mostly valid for heavily over consolidated soil where OCR is greater than 2. Now, it is not mostly valid, it is valid for heavily over consolidated soil. So, m P naught dash root of OCR minus 1 is Qy. Now, let us discuss about unconsolidated undrained triaxial test. We know V naught is equal to Vf is equal to gamma minus lambda ln P dash f, because it is an undrained test. Now, please refer back if you are finding it difficult. Now, we are not going to repeat it. So, P dash f can be written as exp gamma minus V naught upon lambda, and Qf is equal to m into P dash f. Undrained shear strength Su is equal to Qf by 2. So, and if you substitute it, Qf is equal to m into P dash f. So, Qf by 2 will be m by 2 and P dash f is equal to exp gamma minus V naught upon lambda. And for a given soil, m, gamma, lambda are constants. So, what Su is merely a function of V naught, that is the initial specific volume, or we can write in terms of initial water content. W naught is the initial water content. Now, let us say unconsolidated undrained test for NC sample. If it is V naught, it is the same equation we are considering, we have P dash F, but we also have, since it is an NC sample, we can also write V naught is equal to N naught minus lambda ln P naught dash. Now, if you substitute for V naught here, for P dash F can be written as exp gamma minus N naught plus lambda ln P naught dash upon lambda. Now, SU is also equal to m by 2 exp gamma minus V naught by lambda from the previous slide. So, SU can be written as m by 2 exp, we are substituting for P dash F, we have gamma minus N naught plus lambda ln P naught dash upon lambda. And SU can be written as m by 2 exp, if you split this, we have gamma minus N naught by lambda, this one, plus ln P naught dash. Knowing P naught dash, SU can be determined because all others are the part of critical state parameters. For a given soil, these are all constants. P naught dash increases with depth. Why? Because P naught dash is a mean vertical stress, so mean stress condition, and with depth mean stress condition increases. So, since P naught dash increases with depth, the SU for normally consolidated soil increases with depth. So, if you want to prove that SU of NC will always increase with depth, this is the proof, and P naught dash increases with depth. And according to this equation, SU is merely a function of P naught dash because all others are constants. Now, the same exercise for OC sample, SU is equal to m by 2 exp gamma minus V naught by lambda. V naught is equal to V kappa minus kappa ln P naught dash, because this is an unloading reloading case. So, we can write SU equal to m by 2 exp gamma minus, substitute for V naught. V naught will be V kappa minus kappa ln P naught dash. So, that is what is done here. Again, like previous case, we can write m by 2 exp gamma minus V kappa by lambda plus kappa by lambda ln P naught dash. This does not get cancelled off, it is kappa by lambda. Also, we have SU is equal to m by 2 exp gamma minus V naught upon lambda. We can substitute for V naught, that is equal to 1 plus E naught. So, we can write SU equal to m by 2 exp gamma minus 1 minus E naught upon lambda. And what is E naught? E naught can be substituted as G into W naught, because SRE equal to GW is equal to SR into E. So, based on that, SU equal to m by 2 exp gamma minus 1 minus GW naught upon lambda. So, let us try to understand why we have done the previous expression is to understand what is the influence, how much is the influence of initial water content on undrained shear strength. Just to prove that, SU is equal to QF by 2 is m by 2 exp gamma minus V naught by lambda, that is SU m by 2 exp gamma minus 1 plus E naught upon lambda. Let us consider two samples A and B of the same soil with 1% difference in initial water content W naught. So, we are just trying to see this 1% difference in initial water content will translate to how much difference in SU. So, we are considering the critical state parameters, or in the critical state parameters lambda is equal to 0.15 and specific gravity as 2.7. SUA, that is for sample A, we can write m by 2 exp gamma minus 1 plus E naught A upon lambda, and SUB is E naught B, only the initial void ratio there is a difference. Now, if you divide SUA upon SUB, we can write EXP, because m by 2 gets cancelled off, gamma minus 1 plus E naught A minus gamma minus 1 plus E naught B upon lambda. So, here you have SUA by SUB is equal to EXP E naught B minus E naught A upon lambda. Why? Because this gets cancelled, 1 gets cancelled off, it will be E naught B minus of minus. So, that will be plus E naught B minus E naught A upon lambda. We know E naught is equal to G into W naught. So, substituting for G into W naught, we have SUA upon SUB equal to EXP G into water content of B minus initial water content of B minus initial water content of A upon lambda. Substitute for G, that is 2.7. The difference in water content is 1%, so 0.01, lambda is given as 0.15. So, if you substitute that, we will get SUA by SUB is equal to 1.2. So, SUA is 20% more or 1.2 times that of SUB. So, 1% difference in W naught results in 20% difference in SU. So, that is the conclusion. So, a very small difference in W naught will be a glaring difference in SU. So, natural water content in the samples should be preserved as far as possible. When we are doing sampling from the field, it is very important, that is why it is told that it has to be packed properly, and hence we can preserve what is the natural moisture content or field moisture content as it is. Otherwise, it is going to influence the strength which is determined. Now, here its influence on undrained strength is quite high. So, if we do not take care of initial water content, then SU would considerably vary and we will not be getting the condition that is existing in the field. So, that is all for the initial part of prediction. So, we have tried to understand the various equations that can be used for finding out the failure stresses. So, let us try to summarize today's lecture. The relationship for predicting failure state in MCCM is derived. Failure state in drain triaxial test is dependent on initial stress state and M parameter. Equation for peak deviatoric stress or deviator yield stress is expressed in terms of OCR for heavily over consolidated soil. So, we have also found out that Qy and P-y also can be determined for any given type of situation. Undrained shear strength SU is expressed in terms of critical state parameters for NC and HOC. Undrained shear strength SU of NC increases with depth, that we have shown. SU is highly sensitive to initial water content. So, that is important to preserve natural moisture content. So, that is all for today's lecture. We will be continuing the same in the next lecture with more details added to it. All the discussions remains the same, but we will also try to see the prediction of Cu and Cd for NC and OC material or soils, and with respect to the volume change or the pore water pressure also added to it. So, we will see this in the next lecture. That is all for now. Thank you.